Hey, I wanted to talk a little bit today about that offset voltage and how to account for that in a circuit. So I have some control voltage coming in here, and I'm thinking of this as a voltage between -5 and 5 volts, which should be my volt per octave. And then I want to translate that into a much smaller region that is around zero point 0.7 volts and changes a very small amount. And that will be the kind of active region of the transistor that is going to create the exponential function for our volt per octave circuit. But first we have to go from this plus or minus 5 volts to something that has a smaller range and an offset to it. And we can create that compression of the voltage as well as the offset by creating a little network of resistors. It's the simplest way to do it. So let's look at what we have here. So here is the output, and you see it's the confluence of three different voltages. Up here we have plus 12 volts, down here we have minus 12 volts, and coming in here we have the control voltage minus the about 0.5, 0.6 volt drop across this transistor. And they meet at this point here, which is our output. And the easiest way to think about a network of resistors like this is that it's going to be the voltage here is going to be a weighted average of what it is at these 3 points. And the weights on that average are the reciprocals of the voltages. The reciprocals of the resistances, which is also called the conductance. And so on the right side here, we have a simple voltage divider. I put a couple of constant resistors here and a pot that I can trim here to get basically the offset. So moving this up and down has nothing to do with the input voltage, right? It's just going to kind of change the voltage here to move it, net up and down. And then this one here, the ratio of this to this side over here determines how much impact this has on that. Now, I thought that this was going to work, but there's a really fundamental problem here. Okay, so in blue here we have that plus minus 5 volt signal, and then in red here we have the output. You can see it's much smaller, and it's also shifted up about a volt. However, if I zoom in, you can see the error of my design. You see it's only this positive portion that has this curve to it, and it never goes negative. And that is simply because this transistor requires a positive voltage to turn on. I don't know why I spent most of today trying to get this to work and then only realizing very late that negative voltages weren't gonna work. So we can use an op amp as a buffer. And one nice thing about an op amp is that it can go both positive and negative. It also has very little offset voltage, though there is going to be some offset voltage there. And a nice thing about a circuit like this is that we can trim this pot to adjust for that offset and also trim this one to adjust for the kind of volts per octave. So let's take a look at that circuit on my breadboard here. So I've got my power supply powered up. I always make red plus 12 and then blue is my minus 12, right? And the first thing we have here is the kind of control voltage kind of simulation. And so we have this, it's between this positive and this negative, and the value right now is right here. You see it's coming from over there to right here. I have it trimmed to just about 0 volts, right? That comes out of this pot and into the non-inverting leg of this op amp, and then we have from the output to the negative input we have this little jumper, and that makes sure that it's the same. And so we're basically just copying that voltage here, and then we take it over here and across the board here to the center pin on this potentiometer. And so this here is the combined bit of everything. And so we want that to be 0.7 volts. I goofed there a little bit. This I had taken out to measure its impedance, but it's back in the circuit now. So we come out of the op amp here, through this, which trims the the kind of impact that this control voltage has on it. And so you see we coming in here, we have basically 0 volts, and then coming out here, this is where all three of those come together, and right now we have 0.671 volts. And so what we hope that happens is that when I increase this to, say, 2 volts, just this little trim here, this nice 25 turn pot is really easy to adjust. You can really dial things in accurately. That'll be close enough for now. We have about 2 volts there. And now when we come here, we seem to have bumped something. Back to 0 volts coming in, we have 0.684. I think I bumped this guy here and it went negative. So let's look at this again. 0.684, and then when we increase the input to, let's get 2 volts here. Okay, well that's somewhere in there, that's close enough. Now we should see this have increased about 20 millivolts. Okay, well it looks like about 40 millivolts or so. But that's the idea. With the amount of trim that we put here, we can kind of adjust how impactful that first one is. So we could reduce that if we want. It's not. This one is yeah, not very sensitive, but. Well, there you go. From my measurements earlier, I was able to get differences in the output of about 26 millivolts for every volt changed on the input. And that's the basics of what we need for the next circuit, which is this one over here, which is actually going to do the exponentiation in a rather controlled way. And hopefully we can see that next week.